In this video, we're going to look at two important lemmas about subrings. So let's go ahead and state the first of the lemmas. We're going to let R be a ring, and S is a subring of R. And under this situation, we then have that the 0 in R actually belongs to S. In other words, the additive identity of the subring is the same as the additive identity in the big ring R. So how do we go about proving this? Well, first of all, I want to think about what our goal is. Our goal is to show that the additive identity element of the subring is the same as the additive identity in the big ring R. So what we're going to do here is we're going to first of all state that since we know S is a subring, we actually know that S is a full-fledged ring. And what that means is that S has an additive identity element. And we're going to call this additive identity element 0 sub S. And what we want to do is we want to show that 0 sub S is actually equal to 0 sub R inside the big ring R. And here's how we're going to do it. The first thing is that I want to list the things that I actually know about what's going on. I know that for every element inside the subring, 0s plus that s is equal to little s. But I also know that for every element inside the subring, that element also belongs to the big ring R. And so that means I also know that 0r plus little s is equal to little s. And so what that lets me do is it lets me set up an equation based on these two facts. In other words, what we can write is we have this. We know that 0s plus little s is equal to s, which is equal to 0r plus s. Well, that's enough to imply that 0s plus s is equal to 0r plus s, and this is inside the ring R. And now what I also know, because R is a ring, I know that there exists a minus s inside the ring R such that s plus minus s is equal to the 0 element in R. And so what I'm going to do is I'm going to add minus r to both sides of this particular equation. So when we post-add minus s to both sides, we get 0s plus minus s is equal to 0r plus s plus minus s, and this is an equation inside of the ring R. Now, when we think about putting parentheses in the indicated places, S plus minus S is known to be the zero element inside R. So what we now have is the equation 0s plus 0r is equal to 0r plus 0r. Now, it's important to realize that this guy here, 0r, is the additive identity inside the ring R. And so what we now have is that the left-hand side reduces down to 0s, and the right-hand side reduces down to 0r. And this is because 0r is the additive identity in ring R, and 0s belongs to R, and 0r belongs to R. So 0s plus 0r has to equal 0s, and 0r plus 0r has to equal 0r. Now when we look at it, what we now have is the fact that the additive identity in S is equal to the additive identity in R. And what that means is that the zero element in R does indeed belong to the subring S. Well, now I want to turn my attention to the second important lemma. And lemma 2 deals with additive inverses. So again, what we have is R is a ring, and we're going to let S, under the same plus and times, be a subring of R. And then what we're going to say is that for every little element S inside the subring capital S, we're going to have the additive inverse inside R, namely minus S, will belong to the subring. And again, what I want to do is I want to stress what our proof strategy is. So the proof strategy here is going to be to show that the additive inverse of little s inside capital S is equal to the additive inverse of little s as an element of R. And here's how our proof is going to work. The first thing is that we're going to establish some things that we know. So the very first thing that we know is that since capital S is a subset of the ring R, we know that if little s belongs to capital S, then little s certainly belongs to capital R. And since little s belongs to capital R, we know that there does exist a minus s inside capital R, such that s plus minus s is equal to the zero inside ring R. Now the third thing we know is that since S itself is a ring, and the additive identity element in S is the same thing as the additive identity element inside R by lemma 1, we also know that there exists some element that I'm going to call S hat inside capital S, such that S plus S hat is equal to 0s, which is equal to 0r. Now what we're going to do is we're going to put this statement here, that s plus minus s is equal to 0r, with the fact that s plus s hat is equal to 0r. And that's going to let us conclude that s hat and minus s are one and the same thing. So what we do is we start off now by saying that we know s plus minus s is equal to 0r, but s plus minus s, but 0r is also equal to s plus s hat. And that's by the above facts. Now, since s and s hat are both in S, and S is a subset of R, this particular equation is an equation inside the ring R. In other words, what we can say at this point is that we know that S plus minus S is equal to S plus S hat inside the ring capital R. And now what we're going to do is we're going to pre-add minus S to both sides of this. So we pre-add minus S to both sides. And when we do that, we get the following equation. We get minus S plus minus S is equal to minus S plus S hat. And this is an equation inside the ring R. Now again, we can associate the terms however we want, because addition is always going to be associative in rings. So I'm going to put in parentheses there. And the stuff inside the parentheses is known to be the additive identity inside ring R. In other words, minus S plus S is just 0R. So we get this equation inside our ring R. But 0R is the additive identity inside ring R, so this side here is just minus S, and this side here is just S hat. In other words, to finish this proof off, what we now have is minus S and S hat are the same thing inside R, and what that says is that minus S has to belong to capital S, since we already know that S hat belongs to capital S, and that completes the proof.